training and batch. Oh, yes, thank you for the recording, Bill. Awesome. The first talk is Scaling Training and Batch Inference, a deep dive into Ray Air's data processing engine. And we're going to hear this talk from Clark Zinzao, who is a software engineer at Anyscale, working on Ray's data plane and machine learning ecosystem. We're super happy to have you here, Clark. And the next talk is going to be a dual speaker talk. The next talk is called Large Scale Data Shuffle in Ray with Exoshuffle. So lots of scaling with Ray, scaling in different ways than we have seen before. So we're delighted to hear about this. The speakers for that talk will be Stephanie Wang and Jiajun Yao. Stephanie Wang is a PhD student in distributed systems at UC Berkeley, a software engineer at Anyscale, and a lead committer for the open source Ray project. She's working on problems like fault tolerance and distributed memory management. This is some awesome stuff. We got some great speakers for you tonight. Thank you, Stephanie, for being here. And we also have Jiajun Yao, who is a software engineer at Anyscale as well, and a committer on the Ray project. He's interested in making distributed computing easily accessible to everyone. So Jiajun, thank you for being here. We're super thrilled that you're here. And we have the bonus, Jules Damji, who's just a wonderful leader in the field, and we're super happy to have you here. So thanks everybody for being here. And Clark, I'll turn it over to you.
Sweet, thank you for the intro. Yes, also apologies about the light behind me. I'm not quite sure what to do about it, but I think it's been mostly mitigated.
We can see you, okay.
Okay, awesome. I'm happy that I'm somewhat visible. But really the important thing is the slides. So, first, everything looks good. Everybody can see these slides. Always like to double check.
Yeah, we can.
Oh,
yeah.
Awesome. Okay, so my talk today is about scaling training and batch inference. And in particular, it's a deep dive into how Ray Air solves some common scaling problems with machine learning pipelines. And it does a bit of a deep dive into Air's data processing engine, Ray Datasets. Yeah, so let's dig in. So first, a little bit about me. Probably can skim over this because of the excellent intro already given. Yep, software engineer at Anyscale. I've been at Anyscale for nearly 2 years now, and I primarily work on data-intensive computing stuff. So I've worked on Ray Core and Ray's data ecosystem. And yeah, I've been working on this Ray Datasets thing for basically about a year now, which is a lot of fun. First, what exactly is Anyscale for anyone that's not familiar? We are the original creators of the open source system Ray, and it's also its wonderful machine learning libraries built on top of Ray. And it's Ray itself is a unified framework for scalable computing. And our target is scalable compute for AI and Python. And as far as why we do it, scaling is a necessity, and I'll get into that in a little bit. And scaling is hard, which if anyone here has tried to scale up some complex compute, I'm sure you're aware of some of those problems. But we're trying to solve those the hard problems ourselves. So for all of our users, hopefully it'll be easy and simple. First, quick overview of this talk. I'm going to go into why scaling ML is hard. I'm going to go into why Ray Air makes this scaling pretty dang easy. I'm going to talk about this pesky thing called ingest and why it's a common bottleneck, especially as your data scales. And then finally, we're going to dig into how Ray Air solves this ingest bottleneck with Ray datasets. First, scaling ML is hard. For folks that are either familiar or unfamiliar, your typical ML pipeline might look something like this. You have some data loading and pre-processing using your favorite little like Python libraries, such as Pandas, NumPy, Spark, TensorFlow. And then you want to feed that pre-processed data into either training or inference. And when this is on a single node, this ends up being pretty easy. The data is just transferred between these stages in memory. It's pretty dang quick. It's just a memory access, and then you're relatively happy. Your single node training or inference pipeline is humming along pretty smoothly. Unfortunately, we can't just sit there with our single node until the end of time. As data scales, your ML pipeline also must scale. So first, why exactly do you hit the need to scale? Maybe your data doesn't fit into the CPU or GPU memory of a single machine. As you may know, the memory, the available like DRAM, like CPU memory, and available GRAM for GPUs, it is not infinite, unfortunately. And you can exhaust it pretty quick, even with like the highest capacity hardware out there. And also, even if your data does fit, maybe it's a little bit too slow to process data sequentially. And you might run into situations where maybe some of the machine learning frameworks hide some underlying parallelization and make it pretty easy. But maybe your CPU-based preprocessing isn't easily parallelized. Or maybe it's just the hardware constraints of a single machine means even if you can parallelize on that single machine, you're still leaving a lot of potential parallelism on the table, which you can hopefully take advantage of if you scale out horizontally rather than vertically. But first, why can't we just keep getting larger and larger machines, right? Why can't we just keep upgrading until we have some mammoth, like 2000 or like a 200 exabyte memory awesome machine? That sure would be great. Probably pretty expensive. Well, first, the current hardware trends really make this not such a great option. CPU performance in general is stagnating. I'm sure everyone's seen kind of like the all of the popular articles around Moore's law ending, Denrith scaling ending, and in particular, it's stagnating relative to GPUs. And even GPU performance itself is not keeping up with the compute demand of state-of-the-art AI models. And even though CPU and GPU performance are lagging, really CPU and GPU memory are lagging even worse, not really keeping up with the memory demand of these state-of-the-art models. And so this is one of our favorite graphs. This is from OpenAI, and we also have a little custom extension here to the right for additional years. Yeah, I'm sure that's pretty obvious that we tacked on some stuff there. And so this is showing the compute demand of state-of-the-art AI models over the years. And as you can see, this is a crazy trend, basically a 35x increase every 18 months. So even if Moore's law was still kicking and was still working super well, we would not be able to keep up with the compute demand of state-of-the-art AI models. And so really the single machine solution is not a solution at all, even if we were in the happy land of Moore's law actually still being a thing. So you see this, like, this is a massive gap, and the gap's only getting larger. And even with very tailored hardware that's really tailored to machine learning workloads such as GPUs and TPUs, aka AI accelerators or ASICs, we're still seeing like a huge gap there. Simply cannot keep up with the demand with a single machine. So how can we solve this? Maybe with horizontal scaling. This is where distributed data parallel compute can really help us here. For machine learning training, this looks like parallelizing training across multiple GPU workers, also called like distributed data parallel training. And so a quick little overview of how this generally works. Let's say you have a data set consisting of 4 shards. You give a shard to each of the trainers. You might have 1 trainer per node, a couple of trainers per node. Usually you have like a trainer per accelerator on each node. So here we've got 2 GPUs on each node. So we have a total of 4 data shards over 2 nodes, over a total of 4 GPUs. And then you do your typical little training step by step, doing the forward pass, backward pass. But then you also have this gradient sync that you have to do, where you have to average these gradients together at the end of the training step in order for all of your workers to stay in sync, to have the same view of the updated model weights. And so this is a pretty complex operation where you have to basically do this average across all these nodes. And so the common way this is done in a distributed system is using the all-reduce algorithm. So it's an all-to-all communication. It's pretty complex. For batch inference, we scale up by parallelizing batch inference across multiple workers. This is a little bit more simple. This is like embarrassingly parallel. We don't need to have any of this like all-to-all communication. You just take, let's say, 4 shards, map them over 4 GPUs over 2 nodes, and just have each of those workers do inference on its own little shard. Yeah, so it's pretty embarrassingly parallel, pretty easy. So how do you do this when you're trying to scale using your typical ML tech, such as like using Spark for preprocessing, and then maybe distributed torch, or maybe using Horvath for like distributed TensorFlow? that this is kind of what your pipeline ends up looking like. So first, you notice that these are like 2 to 3 disparate systems for your pre-processing, training, and inference. So this is difficult to set up, it's difficult to manage, and it's very difficult to extend with custom functionality, and also trying to basically optimize this pipeline to make throughput as high as possible. It gets pretty difficult. You have this really inefficient data exchange between these stages and systems because you have to persist data when going between, for example, a Spark cluster and a TensorFlow cluster in general, because there's no basically purely like in-memory exchange. This is there started to be development of some like standardized open source protocols and stuff to do in-memory exchange, but it's still between these sort of systems, but it's still early days. And I haven't seen really like good, consistent, stable adoption of those protocols yet. And it's also very difficult to keep your accelerators saturated as data scales and as accelerators get faster. It tends to be pretty tough. And I'll kind of go into one possible solution for that using these systems, and this is coordinated pipelining. So this is where you would have a separate coordinator microservice that's basically orchestrating your pre-processing and training such that you are able to pipeline the data pre-processing for the next epoch with training on the current epoch. And this basically allows you to keep your GPU saturated because you're able to hide some of that pre-processing latency. And as you can see, this is a little bit complex. We've got this whole new coordinator microservice that has to basically manage when we trigger shuffle jobs. And you have to basically sync it with like the current training, point in like the Horobot cluster in order to know when to trigger the new shuffle jobs. And then you still have to basically exchange data through external storage through like, persisting to disk. So this sort of stitching together is difficult to orchestrate. I mean, it was already difficult to manage and operate this cluster of multiple clusters. Now it's even more difficult with this like custom little coordinator microservice. And you also have that expensive materialization to external storage. So not too fun. So how does Ray make this a bit easier? Well, first I have to go into what Ray is. Quick little background. Ray is a very, under the hood, the core Ray system is a very simple and general purpose library for distributed computing. And then on top of that, we have this thing called Ray AI Runtime, which is a very nice unified Python toolkit for scaling ML. And really, it's kind of like can either be adopted piecemeal or as a whole solution for your machine learning pipeline. It runs on your laptop, public cloud, Kubernetes, and on-premise. And yeah, this phrase. It's a layered cake of functionality and capabilities for scaling ML workloads. And so this core Ray system has a pretty powerful programming model. If you're familiar with like Python functions and Python classes, it's basically just your simplest distributed analog of those like fundamental concepts. So for example, a Python function, which is kind of, you can think of as like a pure like input to output, right? Function. We're all familiar with that sort of paradigm. That is the Ray equivalent of that is a task where all that you have to do to distribute invocations of these Python functions and execute them in parallel is add this ray.remote decorator here. And then this function will basically be serialized and run on nodes in your Ray cluster. And then it will return a future, which is basically just like a little handle that's saying like this will contain a result at some point in the future. And you are able then to call ray.get on that, and that will block and wait until that future has been resolved, which basically means that the data has been materialized and then it's been fetched to your local machine. And it's cool. Like I just executed a bunch of tasks in parallel on my Ray cluster, and then I'm able to ray.get the results. For a class, which is the classical deal of like a stateful like programming model, the Ray analog is an actor. So you same sort of thing, the ray.remote decorator on the class, and then now you essentially have a distributed set of classes executing on Ray workers in a Ray cluster. And so the same sort of paradigm where you create the class or you create here the actor, and then you can execute methods using the same .remote API. And that again is an async future API where it returns a future. You can pass those futures to other tasks, and Ray will just basically resolve everything under the hood. And it allows you to basically take these simple, programming language fundamentals of functions, stateless functions and stateful classes, and then, express really complex distributed programs using these simple fundamentals. And then beyond that, you're used to referencing data on a single machine within memory. The analog of that is this distributed object that cannot be mutated, but can be easily passed around between tasks. So you can add the object to the object store, you can fetch it, you can pass it into tasks, give it to actors, and then Ray will basically do all of the data transferring for you using Ray's distributed in-memory object store. So yeah, quick anatomy of a little Ray cluster. So here, the fundamental concepts are we have a head node. You can think of this as like, the master node. And that contains the global control store, which is basically where we store a lot of like the cluster state. And then it's typically where your Python script runs as a user. And then in addition to that, we have all these worker nodes in the cluster. And these worker nodes are in charge of executing those tasks and holding and executing those actors. And one thing that's very fundamental to Ray, and that's pretty unique to Ray, is this decentralized scheduling and distributed in-memory object store. We don't have a centralized scheduler in a single node that schedules tasks. Instead, there's a decentralized peer-to-peer protocol for that. And this allows very scalable scheduling and also very fast scheduling. And beyond that, we also have this distributed in-memory object store where all of the objects are transferred across the cluster using gRPC. The objects are transferred in parallel. And we're also able to get zero copy references to the underlying data for a lot of common data formats, which can be great when you're sharing data on a single node across multiple workers. It allows for basically no expensive deserialization or expensive data copying. You can just reference it in this shared memory object store. So it's super cool. Now back to Ray Air. This is our higher level library that's targeting your ML pipeline, and it has some like higher level abstractions that that will hopefully make a good bit of sense and make it a lot easier to program your machine learning pipeline on top of Ray. It's a scalable unified toolkit for ML applications. One of the core goals is you can take your single node machine learning pipeline code, that really simple little flow that we showed earlier. And then with a one-line config change, you can scale it up to a large cluster. It basically just goes from saying, I want, one worker. Oh, just kidding. I actually want 1,000 workers. So this Ray AI runtime contains several sub-libraries targeting specific parts of your machine learning pipeline, such as data processing, training, hyperparameter tuning, scoring, aka inference, or offline inference, serving, aka online inference, and then of course reinforcement learning. This is all built on top of Ray Core. So an end-to-end example here is basically a full ML pipeline on top of Ray Air. This is showing us loading a data set. As you can see here, that's it. You're just loading a potentially gigantic, multi-terabyte data set from S3. You do a little train test split and a couple of other little pre-processing operations. You then specify your how you want to train the model. Here we're training it with XGBoost. And then finally, we perform our batch inference. So this is basically a single slide showing data loading, pre-processing, training, and inference, all using these high-level declarative APIs. And as you can
I interrupt you?
Yeah.
There's a question.
Oh, sure.
So Shang says, very interesting. For those who are getting started, could you describe the distributed data parallel function, Ray SGD torch trainer with a use case?
I think this is probably the Ray SGD is dating back to an old like V1 version of basically the training element of Ray Air. So could you read that question one more time? What was your specific question about Ray SGD or like Ray's training solution?
Yeah, the question is from Shang. Could you describe the distributed data parallel function Ray SGD torch trainer with a use case?
So I'm thinking that they're asking about kind of like how it works, like basically why is it like a compelling offering? Unless the distributed data parallel I think I could just pull up the chat real quickly. Yeah, if you're asking about how it generally works and what the use case is, it's really just around you want to do seamless scaling of training from like a single node, like on a single GPU, to then data parallel training. And what Ray SGD, now Ray Train, does is it basically makes it a super easy declarative API. It's primarily just orchestrating either a Torch or TensorFlow implementation of like the classic distributed training algorithms, where really Ray Train is just being used as a convenient orchestrator with features such as like checkpointing and nice features such as built-in preprocessors, similar to the sklearn preprocessors. But it's really just more orchestrating the data plane of like distributed TensorFlow and distributed Torch. So the primary use case for that is I'm wanting to have a high level API with still the full flexibility of being able to train any Torch model. And I want to be able to easily go from single node to multi-node, where it's very easy to operate. It's very easy to do things such as like checkpointing, and you get stuff like elastic training on spot instances, stuff like that, where it's very easy and high level orchestration of distributed training. Yeah, I hope I understood your question correctly.
I think so. And Shang and others, feel free to keep putting items in the chat. And if Jules or I can't answer, then we'll definitely raise the question. Thanks so much.
Sure. Yeah. Thanks for letting me know there was a question. Yeah. Sometimes I get rolling on the
keep rolling.
I get rolling. Yeah, sure. So yeah, well, I went back a little bit to go back to the Ray Air overview. So this was like the quick little end-to-end example for a machine learning pipeline. Now, what exactly are we talking about in this talk? We're really talking about Air's data processing engine. So this is the bit that Ray Air uses for its data-intensive computing, and this library is called Ray Datasets. And so it's actually used for all three of these bits of Ray Air's offerings. It's used for both distributed training, where it's for data loading, pre-processing, and the actual like high performance transfer into the distributed trainers. And it's used for scoring or batch inference, where it's the same thing, data loading, pre-processing, and then it's the actual execution engine for doing distributed parallel inference. And then it's also used for reinforcement learning. That's a little bit more of a newer one, and maybe like a little bit of like a side use case, but it's used for some like offline aspects of reinforcement learning. So what is Ray Datasets and why is it nice? Well, you can kind of think of it as Air's data bridge, where between the higher level Air APIs for like, training, scoring, all that stuff, and between Ray Core, Datasets is kind of like the in-memory data bridge where we have some well-defined data formats that we support that we can then offer some pretty compelling operations like data processing operations on top of, geared towards the training and scoring use cases. So for example, Ray Air uses Ray Datasets for distributed pre-processing for both training and scoring. And that's using these common underlying data formats that we then map very efficiently to Ray Core's distributed in-memory object store. And so that completely gets rid of the pesky need to materialize the data to storage between, for example, pre-processing and training or pre-processing and inference. So for example, kind of illustrating this shared in-memory data plane, yeah, between pre-processing and training, all that it is you take that data shard and you basically just hand it off to the training actor. And same thing for pre-processing and scoring. You just, after you're done pre-processing, all that you do is you take that future, that handle to the result that's somewhere in the cluster, and you hand it off to the batch inference or scoring actor. And then it's able to just consume that right out of the distributed in-memory data plane, which is pretty sweet. So first, a little bit more about what Ray Datasets actually is. It's a distributed data processing library specifically geared towards machine learning, and really it towards those two key use cases of training and batch inference. So what this actually means is like it has a really great I/O layer where it has support for many common formats and frameworks. So basically like your favorite file formats like JSON, CSV, Parquet, NumPy, like the MPY file format, as well as really efficient exchange with other distributed task execution frameworks or like distributed data processing libraries like Spark, Dask, Mars, Modin, and also machine learning libraries like TensorFlow, Torch, and then distributed XGBoost. And it offers a few key parallel data processing operations such as map, filter, and shuffle. And then finally, I want to emphasize that the interop with like Ray tasks, actors, and other libraries is super seamless. All the datasets is under the hood is some of those Ray core future objects where it's just references to some data blocks sitting off in your Ray cluster. So you can easily pass that to tasks, to actors in the super obvious way. Like you can just hand off a dataset object to an actor, and then it can start consuming that data, and all of the data is resolved and transferred in a very efficient way. So what are the common bottlenecks that we end up hitting at scale? One of them is ingest, and it's actually one that's a common bottleneck, but it's not the first one that people think about. First, I should define ingest. This is when any of the data loading, pre-processing, and data transfer to GPU workers. So this is basically anything that's upstream from your actual training or your actual inference, basically anything upstream of the GPU. So a little bit more about these scaling challenges. One of them is data sharding. You need to be able to take this potentially very large data set and efficiently assign and transfer data shards to either the training or inference workers. You want to avoid these pesky GPU data prep stalls. So this is referring to when your GPUs are sitting there idle, just waiting for pre-processing or ingest to finish. And we don't like those because that your GPU being idle means you are losing money, whether you're an individual or an organization. And then finally, per epoch shuffling, which is one that's specific to training. And it's one I'll talk about a little bit in the future. This is one particular thing where I think Ray Datasets has a pretty interesting competitive advantage towards or compared to other solutions. So first, data sharding. How do we get this gigantic data set onto trainers? Well, first, what we can do is we basically just, first I should say that just to give the data sharding problem a little bit more context before we get into what Datasets does specifically, this is the sharding problem, which we already talked about a little bit. We need to take this very large data set that's maybe sitting somewhere in like S3, sitting somewhere in like HDFS, and we need to be able to get the data to the trainers on the training nodes fast. And then what's this GPU data prep stalls? As I mentioned, often what you find is when you start up your training pipeline, your trainers are just going to be sitting there waiting for ingest to finish if you're doing training synchronously with ingest. So for example, here, where we have this little ingest stage, and the entire time while that ingest stage is going, the GPU is idle. And then we finish training for the first epoch, but only then we're starting ingest for the next epoch. And all of these little idle GPU gaps are pretty unfortunate, because really like your ingest might be done on CPU nodes, and those CPU nodes are sitting idle during training, and your training is done on GPU nodes, and those GPU nodes are sitting idle while you're doing ingest. And so you're just like wasting, money across the board, and you're just having to wait longer too for training to finish. And then this isn't a problem just for training, it's also a problem for inference. For example, suppose you have 3 stages, you load your data, you pre-process it, and then you perform the inference. If you do this in like a bulk synchronous parallel sort of way over the entire data set, you are going to be waiting this entire time, like here, for example, 200 seconds of your GPUs just sitting idle, waiting for the entire data set to be loaded and pre-processed before you actually perform inference. So that sucks. Now, per epoch shuffling, getting back into why this is nice. First, a little review. Random shuffling of data is great for training. It reduces variance, it improves the generalization of the model, and it, in general, prevents overfitting by decorrelating samples. You can imagine, for example, if your data set was sorted by the target, or aka the label, oh boy, that wouldn't be good for a classification task. If your model saw all like not a cat and then all cat examples, you can imagine how your model would find itself in a woeful, terrible minima that it wouldn't be able to get out of. So that would just be an absolute garbage model. Oh, was there also a new question? I just wanted to check.
No, I was just laughing.
Oh no, it was Jules. It was Jules responding to user. Perfect.
Yeah,
good job,
yeah.
Jules. And so that's just shuffling in general. But per epoch shuffling is when you shuffle on before starting to train at the beginning of every epoch. Not just like before training in general. This is like every single epoch. At the end of an epoch, you reshuffle the data. And what this does is it minimizes the chance that your optimizer is going to get stuck in one of those pesky local minima. Because even if you do a pre-training shuffle, you might get pretty unlucky, and you might have your trainer, or in particular your optimizer, seeing like a bunch of like bad batches. Maybe you get unlucky, you see a bunch of bad batches in a row. But if you perturb those batches between epochs, you are more likely to be able to bounce out of those local minima. So there's a bunch of interesting theory, by the way, if anybody's interested, like email me or reach out on LinkedIn, because there's a bunch of interesting papers that have come out in the last couple of years about this, how per epoch shuffling is pretty beneficial to training. In other words, it yields better model accuracy after a set number of epochs. You can expect to have basically more precision gain per training step and per epoch if you shuffle at the end of every epoch. There are certain data modalities that are more sensitive to this. We found like tabular data for certain like tabular models are particularly sensitive to this, and some are also like less sensitive. Yeah, and the unfortunate thing is when you try to do a fully global shuffle on every epoch, this can really slow down your ingest, because a fully global shuffle, when data doesn't fit into a single machine, is unfortunately a very compute and network intensive all-to-all operation. So here you see this like MapReduce little animation. Thank you, Stephanie. By the way, I stole this animation from you. She's really good at creating great GIFs. This is very memory intensive and very network intensive. It can really slow down your ingest if you're comparing it to just doing like parallel loads from S3. If you add in a per epoch shuffle operation, it can really slow down. And I'll go into a little bit about how you can basically mitigate that. So how Ray Datasets meets these scaling challenges? Well, first, data sharding, pretty simple. Sharding datasets across distributed trainers is as easy as this single call. You just do a little split the data set across, and I want to split into 4 shards, and I want to ensure that all of the shards are equal. So to basically do like a very minimal drop of rows or samples to make sure that all of the shards are equal. And then that's it. And then you can hand those shards off to trainers, which is as simple as passing it to an actor and or basically giving it to a class, and that's it. Super easy. And in additional features, we have this thing called locality-aware assignment of shards to trainers. And what this looks like is you basically pass in handles to those trainer actors, and then datasets will try to do a best effort locality assignment of those shards to the trainer, such that we try to get it so the shard is already on the same node as the trainer when we do the assignment. So for example, let's say you have 4 trainers across 4 different nodes. We have a data set who's then going to have 4 shards. We basically have that these 4 shards are already on 4 of the GPU nodes at the end of pre-processing. which you can also orchestrate yourself to try to get that to happen. And then if you're not using heterogeneous cluster, if you're doing all of your pre-processing and GPU training on just the set of GPU nodes, this can also happen. What Datasets will do is it'll look at like, oh, cool, that shard is already on that node. Let me just assign it to that trainer. So this means that there's no data transfer between the pre-processing stage and the training stage, because we just do locality-aware assignment of the shards. So it just becomes basically a memory reference when going from pre-processing to training, which is good. You know, less transfer over the network is always good. Now, how exactly do we avoid these GPU data prep stalls? We don't want to be wasting money on GPUs. This is basically we break this down into 3 different efforts. Number 1 is you want to speed up your pre-processing. Your GPU is stalled for less time if your ingest just takes less time, you know, which I think tracks. And then another option, if you can only speed it up so far, is pipelining ingest with GPU compute. That's where you overlap your ingest with your GPU-based training or your GPU-based inference. And then finally, GPU overloading is how, for at least the batch inference use case, we are able to try to like really saturate the GPU by basically aggressively sending multiple inference tasks to a single GPU to try to really oversubscribe it and hopefully saturate it. First, how do we speed up processing or pre-processing? A few different ways. The obvious one, it's a distributed parallel data processing library. As you can imagine, it has parallel I/O and transformations. A data set under the hood is just a collection of distributed data blocks. And here is a quick little diagram of that. So basically, each of these data blocks lives on a node somewhere in the cluster, and your RAID data set that you have sitting on your client machine, it's just like a little handle to these distributed block references. Yeah, it's this is all it is under the hood. It's very similar to other libraries like such as like Dask data frames just being partitions under the hood, and same thing with like Spark data frames. So these are just created and transformed in parallel. Like basically that's it. When you call read parquet and you give it like an S3 path to a bucket that has tons of files, or in this case, just 4 files. Here we're saying we want to launch 2 read tasks in parallel that will each read 2 files and produce a block. So here, as you can see, each read task takes 2 files, does the S3 read in parallel, and produces one of these blocks. And so these blocks can exist on different nodes. They can exist on the same node. It just depends on how the read task is scheduled. And under the hood, it's a simple RAID task. It can be scheduled on any worker that has like CPU availability. Like, oh, it has an available core to run this task, so it runs it. And there are actually some optimizations that we have here for making sure reads are load balanced that I'll get into in a bit. And then let's say downstream, we want to do a batch mapper. So this is like a parallel batch mapping operation. Let's say you have 4 blocks and you call like map batches and you map some UDF over it. Maybe it's like, creating a derived column, like a little pre-processing operation. Maybe it's doing some simple like, augmentation to the data, or maybe it's actually, this is your inference function. All that it does is it launches parallel tasks for the blocks and then produces a new block. So that's why a lot of these data set operations are like, they like return a data set. It's because you apply a UDF. All that it's going to do is it's going to map that UDF over all of the blocks in parallel, and then it returns you a new data set, which is just a handle to those output blocks. So basically, the parallelization of I/O and transformations, it mitigates these data prep stalls because it just decreases the time that it takes for those GPU batches to actually arrive at the trainers. So if it takes less time, those prep stalls will be smaller. And then a few quick data plane optimizations to go into. I might zoom by this because I feel like I might be running a little bit short on time. RAID Datasets has a few advanced data plane optimizations. Load balancing read tasks. We try to spread those read tasks across the cluster by default. And this basically prevents common issues with like out of memory errors. We also have locality-aware scheduling of transformation tasks, where we try to schedule those mapper tasks onto the same node where the input data already lives. And what that means, this is a common paradigm called like moving compute to the data. If by moving that compute to the data, we don't have to transfer that data to another node in order to execute the transformation task. So again, it's just like a quick little in-memory reference. And then finally, if we're running out of memory on a node, we have this nice transparent spilling of objects to disk, where we will not get an out of memory error for the array object store. Instead, when it starts to experience memory pressure, we will actively spill the data to the to the disk, and then basically any tasks, downstream tasks, can reference that on disk data, and it'll be transferred to that other node's in-memory store. So basically, its disk is kind of like a backup storage medium for the distributed object store. And so yeah, it results in a faster and more stable array datasets, which is really nice. So next, this is kind of the big one: pipelining ingest with GPU compute. How can we overlap ingest with training and inference? Basically, it's pretty easy. What we do is, instead of this sort of unpipelined setup where you are having these constant little GPU stalls, all that you do is, instead of, like, for example, well, this is basically like the API call, which is dead simple. The read parquet is reading the data from some data source. Repeat is basically repeating that data set for some number of epochs. And then random shuffle each window is doing a per epoch shuffle. And so what this ends up looking like, both the ingest here consists of reading and shuffling. Basically, we have to take the hit for the first epoch because, we got to just like ingest the data. But once we start training on the first epoch, we start doing ingest for the second epoch at the exact same time in parallel. And basically what you see is, if your ingest throughput is the same or higher than your training throughput, you will never see any idle GPU time after the first epoch. So basically, as soon as like you're done ingesting for the first epoch, by like making sure that we're always doing ingestion in parallel with training, we are always able to ensure that when it comes time to train on the next epoch, basically the pre-processing for that epoch, the ingest for that epoch, will be done. So the trainers, all that they should have to do is they should just be fetching data from in memory. So they should basically, it goes from like waiting for that ingest to complete, which might be like 30 seconds, a minute, to instead just waiting for data to be transferred over the node, or over the network. Or even better, with prefetching, the data might just already be sitting there on the GPU node, ready for training. Yeah. And then the inference use case looks pretty similar. We go from this unpipelined, pesky, GPU idle inference pipeline. And then here, what we're doing is we are windowing the data. So what this is doing is we are basically taking this data set read from Parquet files in storage, and we are creating windows over that data. So that's basically like, these are like disjoint subsets. So you can imagine you have a data set of like a terabyte of data and you want to perform batch inference on it. But maybe you only want to map over like a gigabyte of data at a time. And so this will basically keep your active working set of the data set pretty small. So like you could pretty much, this is basically like a streaming processing. And so with this windowing API, you can give a specification for how large you want the windows to be. And then this will create a pipeline such that the loading, pre-processing, and inference stages will basically be pipelined. So although for like these first few windows, we have to take that hit because we just have to basically load and pre-process that first window. But by doing all of these stages in parallel, we can ensure that after that first window reaches the GPU, we can continue to do the loading and pre-processing, for example, on CPU nodes. And then we can make sure that the inference stage, that those inference workers will always be seeing loaded and pre-processed data sitting hot and ready in the object store. So yeah, we're able to hide that loading and pre-processing latency. Finally, GPU overloading, which is basically, and I'll zip through this pretty quick. This is referring to our auto-scaling actor pool, which we have which is pretty nice for inference. So what
Clark,
this does
I think
is
you don't have to hurry. I think we're good for time.
Oh, really?
Yeah.
Sweet. Okay, that's always good for me because I have so much interesting stuff to talk about that I always go long. Sweet. Then in this case, this actor pool is pretty nice. It dynamically scales based on the size of the work queue, and this ensures that as opposed to allocating a gigantic static pool of GPU actors or GPU workers, that we're not wasting these GPUs. So, for example, let's say we have a data set consisting of our favorite number of shards for this talk, 4 shards. And we basically want to start with an auto-scaling actor pool of 1 worker, and we want to scale up this actor pool based on the size of the work queue. So we've got 1 worker available, cool, send it to the worker, and that worker is going to take that block, and we are just going to churn through the batches in that block, and then storing the inference results. And then we see that, oh, that worker is busy with that block, so we scale up another worker. And then we send like the next block to that worker. And then meanwhile, while we're waiting for the 3rd worker to spin up, because again, we all of our workers are busy, the 1st worker completes its work. So then we know like, oh, cool, like we can actually like send this 3rd block to the 1st worker because that worker is idle. And so then we spin up a 3rd worker while the 3rd block is being processed by the 1st worker, and then 4th block sent to the 3rd worker, and then that, basically we complete the batch inference using that 3 worker pool. So that's a very small scale illustration of if you compared allocating a ton of actors, maybe like the same as the number of blocks in the data set. If you have 1,000 blocks in your data set, you might end up really over allocating the number of workers in your worker pool. And by doing this gradual scale up of the actor pool based on the worker queue or based on the work queue, we are able to ensure that we're not over allocating workers, especially in the case that you have like multiple workloads running on a single array cluster. You might have to wait for an actor to become available. Like you might have a fully utilized cluster. And so doing like a static allocation of a pool would be pretty wasteful. And if you block on the allocation of that pool, you might just be sitting there waiting for a long time for really actors that you don't actually need. So making this dynamic based on the work queue size has some advantages. And then in addition to that, we are also able to pipeline the data transfers, for example, from like CPU nodes to the GPU nodes with the actual inference. And we are able to saturate the GPUs with these, with basically fractional GPU requests. So here, as you can see in this like map batches call, we ask that each GPU worker, aka like inference worker, is given half a GPU. So that means we'll have 2 workers per GPU. So as you can see here, we have 2 workers sitting on this 1 GPU, and then we also send 2 blocks at once to a single worker. And what this does is we are basically able to pipeline the fetch for the data for the 2nd block with the inference that's being done on the 1st block. And so this is, again, like trying to hide some of that data fetch latency. And we've actually seen that this combination of the auto-scaling actor pool, pipelining the data transfers with inference, and these fractional GPU requests can get us really high GPU saturation, like really high GPU utilization for these massive like parallel batch inference workloads on a pretty large cluster and a large data set. So finally, on to one very interesting topic that the next talk is also going to dip into, which should be a good bit of fun. Per epoch shuffling. So Datasets has a few different options here for per epoch shuffling. We probably our most interesting one is the distributed option. So this is for a fully global or windowed. If you remember the windowing API, you can actually apply this shuffling on just windows of the data set, which would be, it might be like data that wouldn't fit on a single node, but it's still like might not be like the entire full global data set, which might be super massive. And so with this fully global or windowed shuffle, it's doing a distributed shuffle using a simple map reduce random shuffle. So this is what the API call looks like, right? Pretty simple. And then under the hood, let's say we have 2 blocks. What we do is we send each of those blocks to a mapper task. That mapper task further chunks it up such that it sends 1 chunk per reducer. So we have 2 mapper tasks, each sending 2 chunks to different reducers. Those reducers concatenate those chunks from the mappers and then does its own little shuffle locally. And then finally, that produces a shuffled data set. And so this gives you basically equivalent to fully random shuffling without replacement. So this is our simple map reduce, like, pull-based shuffle. But we've recently added a super hyper scalable push-based shuffle for extremely large data on the scale of hundreds of terabytes or petabytes. And that is exactly what the next talk is about. So definitely stay tuned for that, because that's a very exciting deep dive on that shuffling work. It's super, super cool. In addition to the distributed shuffling option, we also have a local shuffling option. And so this is a little bit more traditional. This is, you have like a on each trainer, you have a little local shuffling buffer. So this is a little local buffer where you can fill in some data, and then you basically randomly pop off shuffled batches from this buffer. So each trainer could have a couple of gigabytes of CPU memory local that it fills up with these samples, and then at a certain point, it decides, okay, I filled up my buffer enough. I'm willing to sample from this buffer. And then it'll pop off these shuffled GPU batches. Obviously, this is not equivalent to a fully global shuffle. Like, this is more just like a pretty efficient local shuffle where the trainer is both shuffling like within its shard, where it's not mixing data across trainer shards on every epoch. And then it's also just basically like not shuffling from the entire shard. It's just holding like a little like 1-2 gigabyte buffer locally. So what this looks like in terms of an API, we've got like these little like batch iteration APIs, like iter batches, as well as some machine learning framework specific consuming APIs, such as like iter TF batches, which gives you torch or TensorFlow tensors, and then iter torch batches, which gives you torch tensors. And here you specify batch size, and you say, I want a local buffer, local shuffle buffer of size 4 samples. So that means we at least have to fill it up to be 4 samples before we start popping off random batches of size 2. So what this looks like, we once again have our 4-block data set. We fill in the first block, and each block here, by the way, contains 4 records. And so cool, we filled up our buffer halfway. We haven't filled it up all the way to the minimum. It's actually, we have to get past the minimum size of 4. We haven't filled it up to 5 or above. So we should fill in another block. We need at least 1 more record before we're willing to pop off these shuffled batches. And then it's cool, awesome. We have 8 records now. 8 samples. We are totally ready to shuffle the buffer in full, which is what we do. We take the entire buffer and we shuffle it, and then we pop off a batch. And so this is a shuffled batch, basically just containing the first 2 blocks of data in the buffer, and then we pop off this like a little like two sample batch. And then we basically said we just shuffled the buffer, so we're able to pop all of these off. We're saying we met our minimum size requirement for the buffer, and we shuffled it. So now we can basically consume each of those batches up until we dipped below. We were about to dip below that local shuffle buffer size of 4. So that's what happens here. We basically pop those first 2 off, and it's like, oh, can we pop another one off? No, we can't, because then we're going to be dipping below that local shuffle buffer size of 4. Which means then we have to wait until ingest is done so we can add another block. And it's okay, cool. We're above that local shuffle buffer size, which means now we shuffle it again. And what this does, as you can see, is although it's like a very limited shuffle buffer size, like we've only basically we're not going beyond 8 records here. We are mixing samples across the entire data set. So there's basically some probability you're going to see a sample in like the later stages of your epoch that actually were from the first block in the data set. So this allows us to get something that's kind of like pretty close to a decent shuffle, because we are with some probability mixing samples across basically the entire epoch's worth of data. And so then cool, we shuffled our full buffer. So we pop and we pop, and then, oh, nope, we're about to dip below the local shuffle buffer size. So we know we have to wait, and then we fill it, and then we shuffle one more time, and then we pop and we pop. And then now we know we have no more data to add. So then we pop those last 2 batches. So that's
Clark,
kind of like
an awesome
yeah.
Visual. 5-minute warning for you.
5-minute warning?
Yeah.
Okay, sure. Sure. I'll go through pretty quick. So what this boils down to is a trade-off between the randomness of the shuffle. With global shuffling, you get a fully random shuffle, and then with windowed shuffling, you're still potentially getting some pretty nice like mixing of data across trainer shards. And it's like it's still better than a local shuffle. But then this local shuffle is just really like not as random. So it's a trade-off between the randomness of the shuffle, which is basically like going to affect the accuracy of your model over a fixed number of epochs, and then the throughput of the shuffle, where with this local shuffle buffer solution, it's just like an in-trainer, like little local shuffle. So you can basically make this pretty fast. I think we got it within we got it to be pretty close with this like particular like buffer implementation, pretty close to being like the same as like the base like raw iterator with no shuffling, in particular with like stuff like prefetching. So yeah, it's basically a simple trade-off, and it depends on your use case, your data set, your model, all that. But we have both options. So a quick zip through some case studies. First, distributed training ingest at Predibase, which is an ML platform company. They had an issue where their training is ingest bound and their models are shuffle sensitive. So they want to have a per epoch shuffle. Their previous solution was going from pandas to then storing in S3, then loading from S3 with Petastorm, which is a data loading solution, open source from Uber, and then basically going from Petastorm and ingesting into Horvad, which is a distributed training solution. And the Ray solution that we pitched and that they adopted was using Dask on Ray, which is taking a Dask preprocessing workload and running it on top of a Ray cluster, and then going directly from Dask on Ray to Ray datasets. So there's no persistence to S3 between those 2 stages. And then ingesting from Ray datasets directly into Ray train, which is basically Ray's distributed training solution, the replacement for Horvad. And the end result was basically that it was 8 times faster than the pandas plus S3 plus Petastorm, even on small data and cluster scales. And so this was a little bit surprising to us that even on these small data and cluster scales, that it ended up being a good bit faster. And so here's like a quick little benchmark showing on a little bit of a subset of the New York City taxi data set in a single GPU instance. The Ray-based solution was a good bit faster, even when trying to basically like do a custom Petastorm solution using its own async prefetching. So basically the Ray-based solution was looking pretty good. Awesome. Another quick use case is a similar problem, distributed training ingest at a large transport tech company. Their training was ingest bound and their models, once again, shuffle sensitive, so it's still looking for pre-epoch shuffling. Their old solution was S3, Petastorm, and Horvad, pretty similar, except with no need for Ray-based preprocessing before S3. And then the Ray solution was still going through S3, but instead using Ray datasets plus Ray train. And their end result was that the Ray datasets ingest was 4 times faster than Petastorm on S3. And they were able to more than double their training data volume. They were able to train basically on more data. And that yielded a 1% reduction in mean absolute error, which for their use case was a pretty big deal. And this was a simulated benchmark that we ran with some synthetic data, kind of modeling their data on 60 nodes with 2 shuffle windows. So this wasn't a fully global shuffle. We windowed it into 2 windows. And we saw basically a 4x improvement in aggregate throughput compared to Petastorm, which I want to stress, we are also doing a lot more work than Petastorm here, because we're doing this windowed shuffle over like 750 gigabyte windows each, way more than can fit in the memory of the machines. And so Petastorm, meanwhile, was just doing a local shuffle. So we were actually doing a bit more work while achieving better aggregate throughput. And then finally, back to Predibase, distributed batch inference at Predibase, they had an issue of it wasn't scalable, kept seeing idle GPUs. Old solution was Pandas and Torch. The Ray-based solution was Dask on Ray once again, plus Ray datasets and Torch. And the end result was 5 times faster, even on these small data and cluster scales. And here they've got the comparison of the results as the data size goes or it gets larger. The reason why, oh, and by the way, this is throughput. This is throughput, not time to execution, so larger is better. The reason why Pandas, their Pandas plus Torch solution no longer shows up for these data scales is because they ran out of memory. They weren't able to get it to work with like the Pandas plus Torch solution. So basically that's another thing. Feasible, the workload was feasible using Ray. And then a quick testimony from an ML engineer at a telematics startup. Ray Air has greatly improved my developer experience through intuitive abstractions like Ray datasets and train. In 2 weeks, I was able to recreate and outperform a data ingest pipeline I built by hand over the course of 6 months. So that's both a testament to awesome performance improvements and also pretty nice developer UX, especially compared to trying to hand roll it, which is good. Whenever I see so many issues every day of users having difficulties with the rough edges, you know, that we're still working with Ray Air. You know, it's still like, you know, it's like a beta product. Every time I see those rough edges, I'm like, oh gosh, it could be so much better. But even in its current state, in its early days, it's still yielding a good bit of a speed up compared to doing this by hand. And developer experience is maybe better than I think when looking at tickets all day of things that are wrong. So in summary, and I'll go quick because I know getting close or slash over. Scaling ML pipelines while maintaining high throughput and high GPU utilization is very hard. And the consequences of not being able to do it is you are not able to train on as much data. You're wasting money on idle GPUs. You know, whoever's in control of your company's budget gets mad at you. You know, all bad things, basically, if you're not able to do it. Ray Air makes it super simple. Ingest is a common bottleneck as data volume scales. And then Ray Air uses Ray datasets as its data processing engine to try and fix some of these ingest problems via features such as distributed data sharding, fast I/O and pre-processing, smart and resilient data plane of Ray Core, which we just inherit, which is nice, and then pipelining of CPU and GPU compute, and finally, efficient and scalable per-epoch shuffling. So a quick teaser of ongoing and future work. As you can see here, we're looking at integrations with distributed pollers to try and be way faster with our tabular data processing. We're looking at NLP and computer vision preprocessors. We're looking at more end-to-end streaming processing, where basically we can stream down to the individual like chunk level for really like memory limited clusters or super large data sets. We're looking at data connectors with different data sources. And then we're looking at some custom stuff with graph neural network training with pretty interesting like graph subsampling and stuff like that. It's pretty interesting. We're looking at optimizing this like last mile pipelining, like transferring from CPU to GPU. And then finally, we're looking at a lot of automatic ML pipeline optimizations. That's automatic tuning of parallelism, of repartitioning, automatic tuning of the batch size for GPU inference and for GPU training. We're trying to basically turn it from its current like imperative datasets processing to a very declarative API, basically through Ray Air. So that's one thing I'm particularly excited about.
Clark, there's so much good stuff. I gotta thank you, and I want to make sure we leave enough time for Stephanie and Jiajun. But thank you so much. This is Ray Air seems awesome. So let's hand it over to Stephanie and Jiajun to tell us all about Exoshuffle.
Thank you, everyone.
Let me just share my slides.
Awesome. And Clark, there's a question for you. Maybe you can chime in on our friend Chris Fregley's question in the chat.
Oh, sure. Yeah, I'll start answering questions. Thank you.
Okay, cool. Yeah, I can get started. Yeah, so thanks, Clark, and thanks, Anya. So today, Jadri and I are going to talk about our work on Shuffle, which Clark already did a really nice preview for. But one of the exciting things that we did actually in the recent Ray 2.0 release was we looked at large-scale Shuffle performance. So basically being able to scale Shuffle on Ray to 100 terabytes or more. Okay, so just a little bit about us. You probably guessed this already, but we're both software engineers at Anyscale. Jadri and I both work on the Ray core team, and our team is kind of supporting the engineers and Datasets, including Clark. So I also am a researcher at UC Berkeley. I'm finishing up my PhD there. And so this project is actually a collaboration with researchers at Berkeley as well. Okay, so yeah, let's take a look first at why we wanted to support large-scale Shuffle on top of Ray. So Clark already gave a nice preview here, so I'll just go through this quickly to kind of recap. So, we can first think about what the broader picture of the Ray ecosystem is. So as you saw earlier, Ray Core is basically this unified framework for scaling Python applications. So it's an open source framework. And to make it even easier to scale AI applications, we have this toolkit called the Ray AI Runtime, or Ray Air. And this is basically a collection of libraries that handle things like training and data processing. And as Clark said, one of the most important libraries here is actually distributed data, since this is kind of what's holding together all of the other libraries. So for this talk, we'll do a deep dive specifically of Shuffle, which is one of the more critical operations that's used by Datasets. So here's basically like a sort of slightly different visualization of the problem that Clark talked about earlier, where we want to shuffle this data set and load it into these GPU workers for training. So this is a distributed training job. We have 4 different replicas, for example, here. And loading the data into these workers is actually a pretty difficult task because we'll have to load this data set from storage into memory. We'll have to shard it across this pool of workers. Eventually, we'll probably want to train it on data that's larger than what can fit in memory at once. And then to improve model accuracy, we'll also want to randomly shuffle the data set before passing it to the trainers. And then finally, we have to pipeline this computation with the training so that we can keep the GPUs busy. So as Clark kind of hinted at earlier, doing this without Ray actually requires putting together many other different systems. But with Ray Air, we can actually do all of this in a single system. And specifically, we'll talk about how this shuffling part works today. Okay, so I wanted to go first into a bit on what Shuffle actually is. So Shuffle is this operation that's used in MapReduce. And it's basically these programs that can be executed in 2 stages. So you have a map stage that applies the same function to each partition in a data set. And then you have a reduce stage that aggregates these intermediate results from the map stage. And so in between these stages is what we're calling the shuffle operation. And it's called a shuffle because we're basically taking one intermediate block from each of the map tasks, and we're moving that block to a different reduce task, as you can see in the figure on the left. So I just want to note here that randomly shuffling a data set also uses this operation under the hood. But for the rest of this talk, when I say shuffle, we're actually going to mean the system level operation that moves these blocks from the mappers to the reducers. So unlike random shuffling, this is actually a generic operation that's used in lots of other data operations as well, such as sorting and group by. So many of us have probably written a MapReduce-like program in Python before. So what actually makes this problem difficult? So the main problems actually come at large scale. And the intuition for this is that as the total data set size grows larger, the number of intermediate blocks that you have to transfer between the map and reduce nodes is also going to grow quadratically. So for example, let's say we have a 100 terabyte data set and we're going to use 1 gigabyte partitions. If we do this naively, we could end up with 10 billion intermediate blocks, and each one of these is only going to be 10 kilobytes. So that's fine if everything can fit in memory, But with 100 terabytes, we can't even do that on a large cluster. So that means actually each of these 10 billion blocks of 10 kilobytes each has to be spilled or written to disk. It has to then be restored to memory and then transferred over the network between a mapper and a reducer. And then finally, it has to be recovered in case there's a node failure and we lose the block. So because this problem is so challenging, people have actually built a lot of systems designed specifically for shuffling large amounts of data. And that includes systems like Hadoop and Spark. So these systems will handle all of those problems of managing and recovering these intermediate blocks. And the good thing about building shuffle systems that way is that they're often very high performance. You have these experts who put a lot of work into specializing the shuffle system towards different application and hardware environments. But the cost of doing this is mainly in this high development effort that's needed to build a new shuffle system. And the fact that shuffle is often implemented as a completely separate system makes it difficult to stitch it together with other systems designed for things like distributed training. So as Clark mentioned earlier, there's other examples of data loaders out there who do data shuffling for you, such as Petastorm. And part of the reason those systems were built is because the existing solutions for data processing weren't enough. And then now, you have these data loaders that are having to rebuild the shuffle operation, as you can see in this example. Okay, so yeah, to handle this problem, we decided to see if we could build shuffle in a more flexible way by leveraging the work that we've done on Ray Core. So to see how this works, we can think about how shuffle systems have been built in the past. And so we'll call these monolithic shuffle systems because they implement the shuffle algorithm directly over these lower level primitives like RPC. And then on top of these, you can have framework developers who are implementing these higher level applications like sorting and aggregation. So in our research collaboration with Berkeley, we built out the Exoshuffle project, which tries to see if we can build shuffle directly on top of Ray instead. So by leveraging Ray Core, we can actually implement scalable shuffle algorithms directly in Python and in only a few hundred lines of code. And also, because the shuffle implementation is just using Ray Core primitives directly, it can also easily interoperate with other Ray libraries like Ray Train. So for example, we can pass the shuffle data through memory to a training worker using Ray's object refs. And so that's exactly what we did. In Ray 2.0, it's now possible to scale operations like dataset.randomShuffle to over 100 terabytes of data and to clusters of more than 100 nodes. So we still have a lot of work to do here, but our initial results show that we can achieve similar performance and scalability as previous monolithic shuffle systems. Yeah, I can stop here for a sec if there are any questions in the chat.
I think the questions are being answered already in the chat.
All right, cool. Yeah. Okay, so yeah, let's take a look now and see what makes this all possible. So how exactly does Shuffle on Ray work? So first, the Datasets library is implementing the Shuffle algorithm in Python, and it's using those Ray Core primitives like tasks and objects to do it. And basically, this program tells Ray Core what computations need to run and how to move data between those computations. And then the Ray backend can actually handle many of the hard parts of the Shuffle execution, including spilling blocks from memory to disk, transferring blocks between nodes, and recovering data that's been lost after a failure. So we can also take a look at how this works out on a cluster. So here we have a Ray cluster of 2 nodes. Each of them has some Python workers, which I'm calling executors on this slide. And each node has a node manager process, which is managing the shared memory objects and task scheduling for that node. So the Datasets library sits here in the application driver, which you can kind of think of as the main program or the entry point for an application. And so this is where we're specifying the Shuffle algorithm. The Datasets code is all written in Python, and for the most part, it's actually going to look very similar to normal sequential code that you would write on your laptop. And that's because Datasets is actually using Ray to execute the data processing tasks in a distributed way. So Datasets will submit a shuffle job by calling a series of remote functions, and we'll show an actual example of this code later in the talk. But from here, Ray core basically sees the application as this task DAG. And here it will actually handle the shuffle execution. So the first step is just to schedule these tasks. In Ray, we have a distributed scheduler that determines where to place the map and reduce tasks according to resource availability in the cluster. So the application driver here will queue the tasks that were submitted by the datasets library, and then it requests cluster resources from the distributed scheduler to execute the tasks. Oh, sorry. And here we can submit these map tasks in parallel to the different nodes since they don't depend on each other. And once all of the map tasks finish, the driver will repeat the same process for the reduced tasks. And Judging will actually say more in the second half of this talk on how the scheduler is actually working under the hood. Okay, so with these tasks scheduled, Ray is also going to handle the dependencies between the map and reduced tasks. So here, each reduced task is going to depend on one output from each of the map tasks. So first, on each node, the map task executor produces results in its local shared memory object store, and the Ray node manager will handle spilling these to disk if the shared memory store becomes full. And so this is also how we can guarantee that there's always a hard limit on the amount of memory being used by Ray. And to execute the shuffle of the data, Ray's distributed object store also handles that transfer of intermediate objects between nodes. So here we scheduled a reduced task on node 2, and so we need to fetch one intermediate result from each of the map tasks. So to do this, the node manager will request one object from the map node, and we can also transfer intermediate results from the rest of the nodes in parallel, and these will then get aggregated by the reduced Python task. So that was kind of a quick high-level overview of the different components involved in Shuffle on Ray. And next we can take a look at how Shuffle is actually implemented in Python. So the key primitive that we're using from Ray core is these tasks and objects, which we can use to create a DAG of dependencies between the map and reduce tasks. So the simplest way to implement a shuffle basically looks like the map reduce program that I showed earlier. We have one map task for each input partition, and then each map task will produce one intermediate result for each reduce task. But there are lots of other ways to implement a shuffle algorithm, and this is actually a pretty active area of research and development. So you don't need to know all of the details of these shuffle algorithms, but you can find out more by reading the Exoshuffle white paper, which we have on arXiv, and that's linked through the QR code above. So the main thing to know is that many of these shuffle algorithms are optimized for large data sets, where the cost of doing lots of really tiny IOs starts to dominate performance. So most of these algorithms involve some kind of merging of the smaller intermediate results, and that makes it so that we can perform larger IO requests during the reduce stage. Here's another variation called push-based shuffle, where we're pushing map results directly to the reduced nodes and then merging them into larger chunks there. So I want to stress that all of these algorithms were actually originally designed and implemented by other shuffle systems. But the cool thing that we found in this project is that we can actually implement a lot of the same basic algorithms, but using Ray core primitives to do a lot of the heavy lifting here. And that made it so that we didn't actually have to rebuild an entire shuffle system from scratch. So to get an idea of just how important it is to pick the right shuffle algorithm, here are some results showing a simple shuffle versus a more advanced algorithm. So on the left-hand side, we're showing the driver memory required. And you can see that simple shuffle actually runs out of driver memory after about 2 terabytes of data. And that's because it needs more intermediate blocks to execute the shuffle. And so those intermediate blocks are adding a lot of metadata overhead to the driver. On the right-hand side, we're showing the total runtime. And you can see that the performance is similar after about 500 gigabytes, but that the push-based shuffle continues to scale past 2 terabytes of data. So in the future, we're also planning to extend Ray datasets to be able to automatically pick the best algorithm in cases like this. Okay, so next we can go through an actual code example. So here, let's get an idea of how one of these shuffle algorithms is actually written in Ray datasets. So here we're going to use basically the tasks and object refs that Clark showed earlier to write this, the diagram on the left. So first we'll submit one map task for each of the input partitions, and we'll use this map.remote syntax to invoke one of these tasks. Each map task here is actually going to return a list of object refs, one for each reduced task. So all map out here is actually a nested list of object refs. And the actual values of these objects are going to get stored somewhere else in the cluster once the map tasks execute. So that means the driver program here doesn't actually ever need to read this data directly. Next, we have to submit the reduced tasks. So we'll take one intermediate result from each map task and pass all of those object refs directly to a reduced task. So Ray will make sure that the reduced task doesn't execute until all of these intermediate results are local. And then in between these, Ray will also spill and restore the objects and transfer them across the network as needed. And then finally, we repeat this process for each of the reduced tasks. And from here, we can just return that list of object refs that we generated where they can be passed to another Ray application. So for example, one way we can actually use those object refs is to pass them directly to a library like Ray Train. And that's actually what Ray Air is doing under the hood. So we can take a look at some code that implements the data ingest example that Clark and I have been using. So here we have a distributed data set that's been lazily loaded into memory from some Parquet files that are stored on disk. With datasets, we can choose to randomly shuffle the dataset at some granularity. And this could be per partition or even across the entire dataset. And then next, we want to pipeline the random shuffle with the training computation. So the repeat call here will produce an iterator that loops over the dataset, and that allows us to perform the pipelined execution. And then finally, we'll just shard this output across the training workers by calling pipe.split. So under the hood, all of these calls are actually just using Ray tasks, actors, and objects to implement the shuffle. And that's what's making it possible to interoperate between large-scale shuffle and other Ray libraries like Ray Train. Okay, so next, I'll hand it over to Jadring to talk about some of the key Ray core features that made that workload possible. I'm also happy to answer any questions that came up before then. Yeah, maybe I can actually stop sharing so that Jadring can take over in the meantime.
Yeah.
Thank you, Stephanie.
Let me share the screen. Okay, are you able to see the screen?
Yeah, we can.
Okay, cool. Yeah, thanks, Stephanie. Next, I'm going to talk about several key Ray core features that actually power shuffle on Ray. So first, I will talk about scheduling. So in order for the shuffle to be performed, the read, map, merge, and the reduce tasks needs to be scheduled in a certain way. Specifically, there are two requirements. First, we want to balance the load to improve the cluster utilization and avoid data skip. And the second, we want to reduce the data movement across nodes. Now, before we dive into different scheduling strategies to see how they can meet our requirements, let's look at the high level, how Ray schedules tasks. So here, let's say we have a driver that wants to schedule a map task. So the first step, the driver will request an executor from a node's distributed scheduler. And the node is chosen based on some scheduling strategy, for example, based on the data locality of the map input data. And the chosen node's distributed scheduler will either grant a local executor to the driver, or will ask the driver to try another node if it thinks there's a better node to handle this, to run this task. And the last, when the driver gets the executor, it will basically send the task to the executor, and the executor will run the actual task. So this is the high level. So now let's see how different scheduling strategy can affect, well, where the task run. So the first scheduling strategy I want to introduce is a spread scheduling. So here, let's say we have 4 read tasks that need to be scheduled. Like in order to achieve load balance, we want to spread the read tasks across the entire data set. So like each node can load equal amount of shuffle data. This is how you can do it in code by specifying a spread strategy when submitting those read tasks. Now let's see how these 4 read tasks are scheduled in a cluster of 3 nodes. So first, you can see the first read task goes to the first node, and the second goes to the second node, and the third read task goes to the third node, and the last one go back to the first node again. So you can see the read tasks are spread among all 3 nodes in a kind of round-robin fashion. So the second scheduling strategy is a locality-aware scheduling. So here, as an example, here, let's say we want to schedule a map task that processes the data loaded by the upstream read task. So the goal is like we want to schedule map tasks to where the inputs are to avoid data movement. And this is how you can do it in code. Unlike the spread scheduling, we don't need to explicitly specify a locality-aware scheduling strategy. Ray will automatically do that based on the location information of input objects. By default, Ray schedules tasks to where most inputs are. So now let's see what happens if we don't have locality-aware scheduling. So here, let's say the read task runs on the first node, and the read data is stored in the local in-memory block store. Now let's say if the map task runs on a different node, then we need to ship the data from the node 1 to node 2 in order to run the map task. So some data need to be moved across the network, which is slow. On the other hand, if we schedule the map task on the same node as the read task due to data locality, then there's no data movement. So the last scheduling strategy I'm going to talk about is node affinity scheduling. So here we want to schedule 2 merge tasks and 1 reduce task. So the goal is like to collocate, merge, and reduce tasks so that reduce task can get output of its upstream merge tasks without data movement. So now let's see first what happens if without the node affinity scheduling. So in this case, the 2 merge tasks may run on different nodes. Then no matter where the reduce task run, some data movement must happen, which is bad. So the solution here is to use node affinity scheduling, which limits which node a task can run. So here is like how you can do it in the code by first defining the node affinity scheduling strategy with the target node, and then use it when submitting the tasks. So one thing to notice here is like we specify soft equals to 2 when creating the node affinity scheduling strategy, so that we can tolerate the target node failure by running the task somewhere else. So let's go back to this example. With node affinity scheduling, the merge and the reduce tasks, they are guaranteed to run on the same node. So as you can see, once they are collocated, no data movement is needed to run the reduce task. So the next feature I want to talk about is the object scaling, which basically enables out-of-core processing. So this is the animation showing that object scaling happens when a running task wants to create some object, but the local object store is full. There are several things about object scaling. So first, object scaling is the process of spilling Ray objects to the external storage to make room for new objects. It essentially makes shuffling larger than memory dataset possible. And for the spilled objects, they are restored when needed. And last, as an optimization, small objects, they will be fused into a single file for performance. And the last feature I would like to talk here is the fault tolerance. So Ray has 2 mechanisms to provide fault tolerance to node failure. The first is task retry, which will rerun the failed task on other nodes. The second is linear reconstruction, which is a feature to automatically reconstruct objects lost from distributed memory by re-executing the object's lineage, basically the task graph that created the object originally. So let's see them in action. So here we have a deck with 2 map tasks and 1 merge task. So let's say currently the merge task is running. It merges the output of map task 1 and map task 2. Now let's say at that point, the first node fails. Because of task retry, we will retry the merge task on a different node. So let's say it's on the 3rd node. But in order to run the merge task, it needs the output of map task 1 and map task 2. But due to the failure of the first node, the output of the map task 1 is also lost. So Ray needs to reconstruct the object by rerunning map task 1. And for the output of map task 2, it's still available in the cluster. So we just need to copy it over. And then after that, the merge task is ready to run again. So this is a rare example. This bar chart basically shows the runtime of a 1 terabyte shuffle chaos test with different number of injected node failures. As we can see, the runtime is not linear to the number of failures, meaning that we don't need to restart the entire shuffle from scratch when failure happens. So to quick summarize, Ray 2.0 supports like shuffling at least 100 terabytes of data. And this feature is available through Ray Dataset and Ray, so you can already try it out now. And in the future, we will focus on greater scalability and automatically out-of-memory handling, auto-scaling, among other features. So those are the links to the Ray Dataset doc and the original Exoshuffle paper. So please check them out if you're interested. Yeah, that's all for the Shuffle talk. So I think any questions that we can answer?
Awesome. Thank you, Jiajun and Stephanie. We probably have time for maybe 1 or 2 questions. I'm amazed that we are on time. So if anybody has a question, feel free to type it into the chat, or we might have time to unmute one person to ask a couple of questions. And also there is there's a Slack channel to ask more questions for our speakers. I think the Slack channel is posted in the chat here, and I will also share it on our meetup page, as well as all of the slides and the video. Gosh, I think all the questions that were asked so far were answered in the chat. We're so lucky we have so many Ray experts to just answer questions as they have come up. So go ahead. Both really excellent talks. Thank you so much to everybody for being here. I will ask the speakers to stay on for just a couple minutes in case anybody has questions, but if anybody needs to leave, feel free, we won't be offended. Thank you so much for being here, and thank you to our partner AI Camp for providing the Zoom call. So this has been really fun and exciting. It's really neat to see the bleeding edge stuff coming out of UC Berkeley and Anyscale, the company behind Ray. So lots of good stuff to look forward to.
Well, thank you, Anya, for inviting us. We were really, really delighted to have these 2 great speakers, 3 speakers share what they have been working with. And I hope that some of you actually want to join the Ray meetup. We have these very technical, in-depth talks on a regular basis once a month. So feel free to join the Ray meetup and join our Slack channel and let us know. We want to hear more about what you want to hear from our meetups. So thanks a lot, Anya. We do appreciate your kind invite.
Yeah, we're delighted to have you. Looks like lots of thank yous from the chat. Yeah, some really great stuff. It's so fun to see how this was kind of designed with scalability from the beginning. Like a lot of the challenges that we've all faced in different frameworks, they're handled here. It's great to see. So very cool. Thanks to Clark and Stephanie and Jiajun and also Jules. Thanks to you all. And for our attendees, check our meetup page. We will post the slides and the video and all the links that were shared.
Thank you, everyone.
Thank
Thanks.
you.
This was fun.
Yeah, thank you.
For sure. Hopefully we'll be in person one day soon.
Hopefully.
Yeah, these were some really great talks and animations, and it's very clear all of the speakers really are interested that we understand how the shuffle is working, like with all these animations. I'm gonna go back over them myself. They're awesome.
I frequently steal Stephanie's GIFs
Yeah, really
for
good.
like blog posts or for talks. They're always so good. Yeah.
Awesome.
Don't you do it like don't you basically create like animations in Google Slides and then just do like a screen capture video or something? Is that how you do it?
Yeah, I've only done GIFs like once. I did it for this shuffle. But yeah, I basically just like created the frozen versions in Google Slides, and then there was like some like GIF creator that I found online.
Oh,
Yeah.
sure. Nice.
Yeah, but yeah, I do everything in Google Slides.
Nice. How many committers are there for the Ray project?
Oh
Oh,
boy.
actually, I'm not sure. Yeah, committers, it's probably less than 100.
Okay.
Contributors, yeah, I don't know the number off the top of my head, actually.
Ooh,
Right on.
GitHub's taken a while. Oh,
Okay,
can you
739. 739.
for contributors?
Yeah,
Okay, and then but people with write access, I hope it's not 739.
probably not much less.
That
Awesome.
would be
Well,
concerning.
I wonder what it is. Yeah.
thanks to you all for the great presentations. I think I'll stop the recording there.
Okay, yeah, thank you.